Assalamu alaikum and good morning, everyone. So we've looked at the definitions of the enthalpy change that are relevant for you in this AS level. Enthalpy change of reaction, enthalpy change of formation, enthalpy change of combustion, and enthalpy change of neutralization. We have also looked at how to calculate the enthalpy change based on experimental results. Okay, next we're going to look at the calculation of enthalpy change based on the given values. Okay, so there will be some known values and some unknown values as with normal calculation. But before we look at how to do the calculation, we're just going to do some theories and concepts behind these calculations. Okay, so the next section would be on enthalpy. All right, so during a reaction, enthalpy changes that take place is due to the bonds that are being broken and formed. Okay, earlier on the very first session for this topic, we said that reactants have a certain energy, products have a certain energy, and when reaction happens, reactants turning into product, there will be some energy change, or we say energy difference between these two values. Okay, energy is usually in the form of heat, and it is needed to overcome attractive forces between atoms. So if you're breaking bonds, usually we need energy, and this indicates that it is an endothermic reaction. Okay, energy is released from the reaction to the surroundings when new bonds are formed. So when you combine two atoms to form a new bond, we release heat. That means it indicates an exothermic reaction. Okay. Next learning objective that we're going to look at is understand that some bond energies are exact and some bond energies are average. Okay, so bond energies can actually be found in your data booklet it's on section 3 of your data booklet. These are the bond energies, and you've already met bond energies before this. It means that it is the energy that is required to break the bond. Okay, so next we're going to look at the specific definition of bond energy. But if you notice that bond energy is they're all positive values. Yeah, they are all endothermic reactions. So there are more on the next page. Yeah, I think 2 pages altogether. Okay, so you notice that all the bond energies are endothermic. So this agrees with what we have just said just now about when bond breaks, we take in energy that is endothermic reaction. Okay. So this is the exact definition of bond energy. It is the energy required to break 1 mole of a covalent bond to produce individual atoms in gas state. So we're going to practice writing down the equation of bond energy based on the definition. Okay, so there's no space just below the definition, but you can find plenty of space at the bottom of page 9. Okay, so I'm going to write down the equation based on the definition. Okay, so first, bond energy, usually I will just write down example, and then bond energy, example number 1. So it is usually written as E of HH. So that means it's the bond energy of hydrogen-hydrogen bonds. Okay, and if we are going to write down the equation that corresponds to this representation or symbol, usually enthalpy change, we write it as delta HF or delta HC, right? Bond energy is also delta H, but we don't use that representation. Okay, so it is the energy required to break 1 mole of a covalent bond. So that means 1 mole of H2 gas is being broken. So if you just imagine that I'm breaking the hydrogen-hydrogen bond, I will get two hydrogen atoms. Okay, individual atoms in gas state. Everything must in gas state. So I'm breaking the hydrogen-hydrogen bond and also forming atoms in gas state. Okay, so that's one example. A second example, if we look at the bond energy of a N triple bond N. Okay, it must also be in gas form because that's the definition of the bond energy. So to write down the equation for this, you can always draw out the bonds, no problem, but I like to write it without showing the bond. Okay, there is no problem with that as well. Again, we are breaking 1 mole of nitrogen bond, nitrogen triple bond between 2 nitrogen atoms in gas state will be broken down into 2 individual atoms. No plus, no minus, because it is an atom, therefore neutral. Okay, no charge. And it has to be in gas state. Okay. Now, so far we've used examples for bonds that are in gas state. What if, okay, what if, this is just a scenario, what if the question says bond energy of bromine liquid? Okay, can I use the value BR here? Is that bond energy? The answer is no. The reason is because of that liquid state. My bromine must be in gas state first. Okay, so the bond energy, just write down the bond energy of Br2 liquid cannot be identified. We don't know. Okay, but what we can do is first we convert bromine, which is the liquid at room temperature, into bromine gas first. Okay, and this process is called enthalpy change of vaporization. So there will be some value to this conversion. Okay, when you break the intermolecular forces between the bromine molecules in liquid state to change it into becoming a gas, you need energy. Okay, and that energy corresponds to vaporization. Okay, now that our bromine is in gas state already, then only you can use the bond energy to convert it. Okay, sometimes bond energy is called dissociate because we are breaking the bond, we are dissociating the bonds. Okay, so the dotted line indicates where the bond is being broken. So if I have bromine gas already, I can then dissociate it into, again, 2 bromine atoms because of the formula Br2. It is a diatomic molecule. 2 Br atoms, which is also in gas state. And this process, the second process, is then called the dissociation of Br, or bond energy of Br. So the value would be about 193. Okay, so if you were to ask me what is the energy required to take in to break the bromine-bromine bond in gas state, then I will say it's 193. Okay, but if you ask me what is the energy needed to break the bromine-bromine bond in liquid state, I cannot do that. Okay, I have to add in the vaporization first. So that's why for this part of this topic, the state symbol is extremely important. Okay, right. So that's definition. We now move on to the values. As I said, all values of bond energy are positive. They are endothermic. You need energy to break the bond. Okay, the values for bonds are for gaseous reactants. Remember, if you have solid or gas, like the example I show you, I've shown you in the case of bromine, then you have to convert the state into a gas state first. Okay, values are average. So you have to be careful with using these values. These numbers that you have here, they are only average values. They're not the most accurate values, okay? Later on, you will see that we will be using these values in our calculation. That's a good estimation, but it's not the best best method to calculate enthalpy change. The reason is because the values are average. The thing about bond energy is that it depends on the molecular environment. What do I mean by molecular environment? The energy of a certain bond is affected or dependent to the other atoms that they are connected to. For example, here I have an OH bond in water and an OH bond in methanol. Now you may argue with me, they are both OH bond, but because they belong in a different molecular environment, this OH bond is attached to another hydrogen. Whereas for methanol, this OH bond is attached to a carbon. So that's a different environment already, even though the bond is the same. So strictly speaking, the bond energy values are different. Okay, now if you look at the data booklet, there's only one value, and that value is the average. Now, where is my OH bond? Is there an OH bond here? Ah, here. OH bond 460. Okay, so this only represents an average value, but it's not the most accurate value. It's not the most accurate bond energy for OH in different molecules. Okay, OH in water will have a different bond energy compared to OH in alcohol or OH in carboxylic acid. Okay, but you know, if you don't have anything, you don't have any other values, then of course you would just use this bond energy value, the average one. But again, they're not that great. They're not the most accurate. So you would expect your values would be a little bit different. Okay. Right. So that's what I've already explained to you. Just have a read again later when you come to revise what you have covered for today. Okay, this is something that's not new to you. In topic halogenoalkane, I think it was mentioned to you already that the higher the bond energy, that means the more energy is required to break the bond. So the bond must be strong. Okay, the shorter the bond length. Okay. Oh, okay. So this is also related to the strength. of the bond. If the bond is strong, the length is also short because there are more overlap between the orbitals, right? Therefore, the covalent bond is stronger. So that's the same. We're talking about the strength. Okay, so that's about bond energies. We've already, well, briefly looked at how to write down the equation. Okay, next we are going to go into this concept called the Hess's law. So Hess's law is a method or a concept that we use to calculate enthalpy change values. Okay, so it is like a energy cycle. It looks like an inverted triangle. I'll show you shortly. And you use it to carry out calculations using, oh, it's not mentioned. So you use Hess's law to determine enthalpy changes that cannot be found by direct experiment. Okay, so you either use this or you do calculations using the bond energy data. Next, Hess's law. So Hess's law cycles are used to measure the enthalpy change for a reaction that cannot be measured directly by experiments. Okay. Instead, alternative reactions are carried out that can be measured experimentally. Okay, this is an example of a typical Hess's law, but later on, or energy cycle. Okay, later on you will see that it's a little bit more complicated than the general energy cycle. Okay, so as I said just now, it looks like an inverted triangle. This arrow have direction and value, okay, size, but you don't have to draw the arrow based on the size, okay, but the most important thing is the direction. The moment you change the arrow, the value will also change in sign. Okay, so what is Hess's law trying to tell us? So if I have an experiment or a reaction that starts from A to go to product B, okay, my reactant to go to product B, and I call this delta H. So that's the enthalpy change that I want to find, okay? But I cannot measure directly the enthalpy change of this reaction for many reasons, okay? One of them may be because of flammability. You can't put your thermometer straight into the direct heat, okay? So many things, right? But Hess's law is saying that no matter what route I take, the value should be the same. Okay, so I want to go from A to B, but I cannot find delta H. What I can do is take an alternative route that goes from A to C and C to B. So this is like addition of vector. Yeah, and I label reaction A to form product C, sorry, reactant A to form product C is labeled by delta H1. So because it's a general reaction, right? So I'll just write down delta H1. And then C to B is represented by delta H2. Now, if you have learned vector, you would agree with me and say AB is equals to AC plus CB. It's the same, right? Starting point the same and ending point the same. And path one is directly going from A to B. And then the second path is the indirect route. Okay. So if I want to work this out, say I have numbers to this, there are numbers to this enthalpy change, okay? Delta H is equals to delta H1 plus delta H2. Okay, now I just want you to know sometimes the missing information is not the one on the top equation. Okay, sometimes the missing equation is maybe A to C, delta H1. We don't know what delta H1 is, but we know what delta H is. Maybe 10. Delta H2 is, say, 20. Okay, so I'm just playing with numbers here. Okay, if the question wants me to find the energy to go from A to C, which is my delta H1, all right, I can also do this. Okay, so that's my resultant force. So my first vector would be delta H plus delta H2. But you have to be careful. The arrow now has been changed. If you are changing the arrow, you must add a negative sign. So it is now 10 plus negative 20 if I want to go from A to C. Okay, whenever you change the direction of your arrow, your sign changes. Okay, so that's a general example of Hess's law or Hess's cycle, sometimes called energy cycle. So this is what Hess's law is. The total enthalpy change for a reaction is independent of the route by which the chemical change takes place. So whether you take the direct route, which is this one, direct route, sorry, A to B, direct route, and that's represented by delta H. Indirect route is A to C, C to B. So that's delta H1 plus delta H2. Okay, so here's an example, a real life example. Okay, so instead of having, A, I realistically have my reagents, okay, going to products. Actually, this Hess cycle contains 3 equations. The first equation is this, hydration. Okay, so hydration of no, it's not hydration. It's not enthalpy change of hydration. So okay, so that's one equation. The second equation is if I dissolve my copper sulfate in excess water. So this is what we call an enthalpy change of solution, which you haven't covered yet, right? To give out aqueous copper sulfate, and the enthalpy change that accompanies that process is negative 66.1. Whereas the third equation is here. If I dissolve CuSO4.5H2O with excess liquid, it would form an aqueous copper sulfate solution. And this reaction, the third reaction, is represented by the value positive 11 kilojoules per mole. Okay, so this is the enthalpy change of delta H solution of copper sulfate with 5 moles of water, and the value is plus 11. The one on the left is delta H solution. Don't worry about delta H solution because that will be covered in A2. Copper sulfate solid. Okay, or the other one I didn't do the state symbol. Okay, so I would just like to be consistent. Okay, so then I don't know delta H reaction. That's what I'm going to work out. Okay, so what happens? Usually we like to keep the reactants separate and the product separate. Okay, so that means you have to have a big arrows showing the nice inverted triangle. If your arrow is small, you will get confused with your arrows later on. Okay, Right. So delta H reaction is the one that we want to find out. Okay. And I will call that X because we don't know, unknown, right? Enthalpy change of solution of copper sulfate, I will call it A. Just to simplify it, okay? But the actual, the more specific enthalpy change that comes in this reaction is enthalpy change of solution, okay? And then the third one, I will label it as B, enthalpy change of solution of CuSO4.5H2O, okay? So from here, I can equate that X, okay? X is that one, going from reactants to the products of the top equation, okay? X is equals to A plus negative B, okay? So notice that the arrow in B has been changed. Actually, B is supposed to be go down, right? But because I want to equate the three arrows and to find the value of the unknown enthalpy change of reaction, I just reverse the arrow and therefore reverse the sign, okay? So X is equals to A plus negative B, okay? So A minus B, all right? And then I just put in the numbers. What is A? A is negative 66.1 minus B is plus 1. Okay, and after you calculate, I know it's already been done for you, but I just want to show you the process. Okay, it's sorry, it's negative 77.1 kilojoules per mole. Units is important. Okay. So I like to do this with A, B, and C, okay? It's easy if you are already prepared with the Hesss cycle or energy, what do you call this? Energy cycles. Yeah, it's called energy cycles, okay? Moving on to the next one. So this is just an explanation why we need to have root A and root B. Why can't we just calculate X straight away? It makes our life easier, right? You don't have to carry out two separate reactions only to find X, okay? The reason for this is that it cannot be done experimentally because it is not easy to measure the temperature change of solids, okay? So you see here, it starts from copper sulfate solid and into CuSO4.5H2O solid. So you can't really find the temperature change, okay? So what we do is that we dissolve in excess water to form a solution of copper sulfate, and whatever temperature changes that was made will be easily recorded, okay, because it turns into a solution. You just put in the thermometer into the solution. Okay, next is using bond energies, the one that that we were talking about earlier. Okay, sorry about that. In this learning objectives, we are to use bond energies. Delta H positive is bond breaking to calculate enthalpy change of reaction. You are also to understand energy transfers occurs during chemical reactions because of the making and breaking and making of chemical bonds. Yes, that's the idea behind enthalpy change. Okay, so if the question asks you to calculate the enthalpy change from bond energy data, this one, using this data, okay, You only do it if there is an instruction. You cannot always use bond energy data for everything, because this bond energy data are just average values, right? Okay, the formula is easy. That summation stands for the total bond energy of your reactants minus the total bond energy of your products. Okay, so there are actually two methods here. First method using bond energy. Second method is using the Hess's law or the Hess cycle. Okay, so let's start with the formula. It says sum. Oops. If you're wondering what that symbol is the sum of all, sum of all bonds in reactants, okay, minus the sum of all bonds in products. So I would divide this into two separate calculations just so that you don't get them mixed, okay? So obviously these are your reactants, right? All we have to do is count the number of bonds, okay? Because the value that we get is per 1 mole of bond, right? So let's start with reactants first. In reactants, we have the nitrogen and triple bond N. So that's just how many nitrogen do we have? And triple bond N is just one. Okay, so the value is 944. Okay, I would just write down 1 times N triple bond N, which is a positive 944 kilojoules per mole. Next is hydrogen bond. Be careful, you have 3 hydrogen bond. So that's 3 times H single bond H, and the value of H single bond H is positive 436. 3 times 436, right, is something. 3 times 436. 1308. Remember that when we do enthalpy change or bond energies, the formula, the units is kilojoules per mole. Okay, so that's your reactants done. Nitrogen done, 3 mole of hydrogen also done. We move on to the products. So there's only one product, but be careful of the bond type. Okay, so NH3 has this shape with a lone pair. Okay, we don't count in the lone pair. We're only interested in the NH3. In one molecule of ammonia, we've got 3 NH bonds. But if you look at the mole ratio, the stoichiometric ratio, we have 2 moles of ammonia. So that means if 1 mole has 3 bonds, 2 mole would have 6 bonds. Okay, so that means it's 6 times NH bonds, and that comes out as 6 times 391. Okay, so that's 2, 3, 4, 6. And then we also total up the reactants, which is 944 plus 130. Correct. 436. Yeah, okay. 944 plus 1308 is 2252 kilojoules per mole. Okay, but that's reactants. Products is that total of products. Sorry. Okay, so please just help check my calculation again, yeah? Lastly, using the formula, delta H, so if we want to find the enthalpy change of this reactant, we have to take the bond energy of the reactants, okay, divide by the bond energy of the products. So how do we do this? I'll use a different color so you can see. Delta H R, I'm just going to call that delta HR of this equation is equals to 2255 minus 2346 kilojoules per mole. And that should come out as negative. Where did I go wrong? 225. 3 times 436. To 252. Sorry, this should be 2252, and then I will change it here to 252 as well. Okay. So the answer should be negative 94 kilojoules per mole. Only use this formula when the question says to use bond energy. Okay. The second method is where it starts to get a little bit tricky. Okay, this is where the Hess cycle comes in. So what Hess cycle was, remember that you have something here and then reactants to go to products, and from the box on the top left is also a reactant to go to another product for the second equation, and for the third equation is from the box on the top right going down into its products. Okay, so you would imagine we have to construct our own Hess cycle. Okay, the question is the same, right? I want to find the enthalpy change when nitrogen reacts with hydrogen to form ammonia. Okay, so that we just call this enthalpy change of reaction, right? I usually write it as delta HR, which is X. Okay, and then I will label my other equations with ABC later on to make it easier. Okay, right. So what I'm going to do is to write down the mini equations for the values given here, because these values are the ones that are going to help me find X when I have constructed a correct, balanced Hess cycle. Okay, so let's start. I will try to color coordinate them, starting with purple. The first value that I have here is the bond energy of nitrogen-hydrogen bond. So that means in terms of equation, it is the energy required when I break 1 mole of NH bond to form atoms. So that's nitrogen and hydrogen, no molecule, no N2, no H2. It has to be atom, okay, in gas state. So that's my equation A, and the value for this process, breaking of NH bond, is 391 kilojoules per mole, okay, when I burn 1 mole or 1 piece of NH bond, okay. Secondly, EHH here means the energy needed when I break 1 mole of H2 bond, because it's HH, into atoms, no charge, in its gaseous state. So that's just breaking the hydrogen into 2 hydrogen atoms. So what I can do is 2 H atoms, no charge, because it is an atom. It's not an ion. Okay. And I will label this equation B. That means I need 436 kilojoules every time I'm breaking 1 mole or 1 piece of HH bond. Third and last equation is the bond enthalpy or the bond energy of nitrogen, N2, which consists of a triple bond, right? So 1 mole, it is the bond, it is the energy required to break 1 mole of bond, which is N2, into its gaseous atoms. Okay, because I've got 2 nitrogens, so obviously I will get 2 nitrogen atoms. I can combine them to give 2 nitrogen atoms, and this equation I will call it C. Okay, so now you see I have equation X on top, equation A, equation B, equation C. I have to prepare a Hesss cycle. A Hesss cycle looks like this. Something, okay, no. Something here in the reactant goes to the product, and then there's something there, okay? So this is the general shape of a Hesss cycle, right? I've purposely omitted the arrow here because it can go up, it can go down, right? So how does it work? First, I start with X on top of the Hesss cycle, because usually but not all the time, usually the unknown is written as the top equation here. Okay, so I will do that, and I will use black. So I want to find the reaction, the enthalpy change of the reaction between nitrogen plus hydrogen, 3 moles, to form 2 NH3 gas. And this is my X that I want to find. Okay, next I am going to put A onto this Hesss cycle so that I get an inverted triangle. Okay, so please follow me here. Okay, NH bond, I have to find in each of the reactants or the product where my NH bond is. And it turns out that I have an NH bond in the product of my equation X. Okay, so what I can do is 2 mole of NH3. What I can do, sorry, so I will do this. My equation A says that when I break my NH bonds, I will form nitrogen plus hydrogen atoms. However, be careful here. I have to count the number of NH bonds, which is the same like what we did in the previous page using formula, but this one we use Hesss cycle. Okay, so I've got 6 NH bonds, right? So that means 6 times of A. Okay, so you just imagine I multiply this by 6. So I get 6 NH bonds to form 6 nitrogen, and how many hydrogen will I form? Yeah, okay. So I will also have 6 hydrogen, right? Sorry, my nitrogen is not 6. I've only got 2 nitrogen, okay? But 6 bonds, all right? My nitrogen, I've only got 2 here. Okay. Next, so that's my, I'll just put a small tick here. A has been drawn into the Hesser cycle. Next, B, okay, I have H2 to form 2H. Now, again, I have to go through each reactants and products in this Hesser cycle, and I can see that I've got a hydrogen there on my reactant. Okay, so let's see. When I break hydrogen bonds according to equation B, I will form hydrogen atoms. Okay, so that's my B, right? But B is 1 mole of hydrogen. 1 mole of hydrogen bond. Here, I've got 3 moles of hydrogen bond. That means I have multiplied my equation B by 3. Okay, so that is represented by 3B. Okay, again, small tick. It works out nicely. You see here, if I break 3 bonds of hydrogen, I will get 6 hydrogen atoms. Okay, don't get confused. I'm breaking this bond H. That's why every bond I will get 2 hydrogen atoms. If I have 3 bonds, I have 6 hydrogen atoms. Okay, if you have to draw it out to help you not get confused, please by all means do so. Okay, A, B done, X done. I've already put equation X. I've done A, I've done B. Next is I have to put C into my Hesser cycle. Now, again, C is nitrogen, N2, and I've got N2 here, right? According to equation C, when I break 1 mole of nitrogen bond, I get 2 nitrogen atoms. Okay, so that's C. All right, can you now see that this is a Hesser cycle? Yeah, I have purposely written down in simple terms X, A, B, C. The number of moles is important because you will have to multiply your value. Remember, enthalpy change of reaction is dependent on the stoichiometric numbers. If it's no longer 1 mole, you have to multiply it. Okay, right. So based on this Hesser cycle, okay, now I would just like to label them, right, using this representation to get you used to it. Okay, starting with C. C is actually the bond energy of N triple bond N. Okay, B is 3 times the bond energy of H. H, A in purple, is 6 times the energy of NH. Okay, so to work it out, now I haven't got space. You can just continue, okay, but I will do it on the side. Usually, I will just use maybe a different color so that you don't get confused, okay? So there's root 1 equals to root 2. If you are confident in your Hesss cycle already and you're great with vectors, you can just see that x is equals to c plus 3b plus negative 6a. Okay, I repeat, if you can see it from just these arrows, okay, x is equals to c plus 3b minus 6a. Why do I minus 6a? Because do you notice that I have changed the direction of my arrow, my purple arrow, okay? But I don't change it in the diagram, okay? I just change the symbol, right? If you don't like that, I hope you can see this. Imagine I have a big arrow here. That's my root 1 equals to x plus 6a. That's my root 2. Okay, so this one, root 1, is equals to root 2. Right, let's see. Root 1 is c plus 3b equals to x plus 6a. Rearrange because our unknown is x. Okay, if I rearrange, now I'm going to just use black. X is equals to c plus 3b minus 6a. This is what I was talking about just now. Okay, so then I just put in the numbers. What's c? C is my enthalpy change of n triple bond n. That's 944. 944 plus 3b. What's my b? Is my bond energy of hydrogen bond, 436. So then I take, 3 times 436, okay, minus 6a. My a is my NH bond here, which has a value of 391, okay? Minus 6 times 391. So I've omitted all the units, okay? Then, is it possible for me to move? I'll make it smaller so that I'll have space, okay? And so x should equals to negative 94 kilojoules per mole. Okay, can you check your calculation again? And then you can see that the answer is the same as your method 1. Okay, of course, I know you will say to me method 1 is so much easier because you just count the number of bonds and then you sum it up for the reactants and then the number of bonds for the products and you just minus them. Okay, but you cannot run away from Hess cycle. You need to be able to draw construct your Hesss cycle correctly. Okay, make sure that they are balanced. Things like multiplying it is also important. Okay, and what else do I want to talk about here? Okay, so if you want to copy this down, please pause this video now. Make sure you understand what is happening. Okay, now I know this is your first time seeing a Hesss cycle. Please don't panic. If it doesn't make sense to you, go through it again, revise again. Okay, but if you still don't get it, it's not the end of the world, because in the next lesson, I will show you more examples of Hesss cycle, and there are many variation of Hesss cycle that you are going to come across with, and only with drawing and doing it so many times, then you will be able to understand or finally follow what's going on. Okay, so don't give up just yet if this doesn't make any sense to you. In the next slide, it's just showing you, in general, when the question asks you to find the enthalpy change of a reaction given the bond energies, and they ask you to draw an energy cycle diagram. Okay, you can memorize it, but I don't like memorizing Hesss cycle. I like to construct it based on what's given already. Okay, but in general, here's what you have. On the top left, you have reactants. Okay, you compare to our Hesss cycle, we've got reactants here. Yeah, reactants of what? Of my equation X, which is what the question is asking for. Okay, we go back. The products, right? I have products on the top right. Okay, and then at the bottom, we've got gaseous atoms of elements. So let's check if we've got that. Atoms, atoms, and in gas form. So we are doing the correct Hesss cycle. Okay, so if you just imagine there's a box here, there's a box here, and there's another box here, and then arrow like that. Okay. Okay, so I will leave you all on this slide. Okay. Please, again, go through it if you need to read your textbooks, if it helps. But if it still doesn't, make sense to you, just wait it out. Okay, we'll have a few more examples on Hesss cycle. Okay, so before I go, I would just like to remind you again to fill in the questionnaires in the Microsoft Forms. The link can be found in the description box below. Okay, Assalamu alaikum, and thank you, everyone.